Hello everyone. So we're going to share with all of you about our discrete math project, which is Planar graph. So my name is Muhammad Arazak Zikri bin Hamazah and my matrix number is 222641. And what is Planar graph? So Planar graph basically are a graph that can be drawn in a plane without any intersecting edges except at the other points. So in a simple term, a planar graph is a graph that can be drawn in a flat surface without the line, which is the line that connect from a vertices to another vertices, must not overlap to each other except the point that they meet each other, which is at the vertices only. So that is basically what a planar graph is. So when the requirement is fulfilled, the graph can be called planar. And after that, we're going to the basic properties of the planar graph. So we have provide to all of you 5 of the basic properties of the planar graph. So for the first one is the faces and the region. So what is faces and region? So faces and region is a portion of plane that enclosed by edges. It is basically the area that is closed by the line. So as you can see at the graph that we provide down here, A, B, C, D graph. So there is two type of region, which is outer region and inner region, which is the inner region is F1, F2 and F3 that you can see it is within the graph itself, and the F4 is the outer region. So basically any graph that can be drawn must have one outer graph, which means you have to calculate all the inner graph and just plus one. So that is the region, which is that you can call area. And number 2 is the crossing number. So crossing number is basically just a minimum amount of edges crossing each other in a planar graph. As you can see at the graph that we provide, also there is no the crossing number for the graph is 0 because there is no crossing from all the line. So for a graph that can be called planar, that we understand before, is the crossing number must equal to 0. So if the crossing number is not equal to 0, the graph cannot be called as planar. For the next basic properties is the graph connectivity. So graph connectivity is a path that join pair of vertices. Basically what it means is that a graph is linked by the line, which is, as you can see in the example we provide, A to B, there is a line that connects the both of it. A graph is considered connected if there is a path between every pair of vertices in the graph. So if a graph is not connected, it may consist of multiple disconnected components, which is cannot be called as a graph lah. Next, we go to the fourth properties of the planar graph. And for the fourth one is the color graph theory, which is we only need 4 colors to color vertices with no 2 adjacent vertices having the same color. As you can see in the picture that include here, there is no 2 areas that adjacent to each other that have the same color, and the minimum color number that needed to fulfill the requirement is only 4. So if the requirement is fulfilled, it means that the graph can be called as planar. And the last one is the embedding. So embedding is an arrangement of its edges or lines in the planes that no 2 lines cross each other except at their common endpoints. So embedding can be called as the alternative way that we can draw the line so that it not cross each other. At the left one is the one before we draw the embedding style, which it cross each other and cannot be called as planar graph. And the right one after we do the embedding, which we can see that the one of the line is drawn at the outer way so that it not cross each other. So the crossing number is equal to 0 and it can be called as planar graph. So that is the embedding. So we already know about the basic properties of the planar graph, so we can jump to the theory and the application after this.
Hello and good day everyone. In this segment, I will talk about 2 theorems. These 2 theorems are the fundamental of planar graph. The first theorem is Euler's theorem, or Euler's formula. This formula was developed by Leonhard Euler, which is a Switzerland mathematician and physician. This formula was developed in 1750 and it is discovered while Euler was solving a polyhedral problem, which is Königsberg bridge problem. While solving this problem, Euler explored the relationship between numbers of vertices, edges, and faces in polyhedra, which lead to the development of Euler's formula, which is V minus E plus F equals to 2, while V represent the vertices, E represent the edges, and F represent the faces or region. This formula can be applied to all polyhedra, while there is no crosses between edges in the polyhedra. And on this page, I will show to you the example of Euler's formula usage. As we can see on the purple polyhedra or diagram, we can see that there is multiple edges and vertices and region. And as we can see that outer region also count into the formula. And as we can compare between the example 1 and example 2, the final result will always be number 2, no matter how many vertices, region, or edges. As we can see in the second example, there are only 3 regions, while there is 4 in the first example. And the numbers of edges also different in both examples. And in this topic, in this page, the usage of representation are different from the formula that I just told you just now, which is N represent the vertices, M represent the edges, and R represent the regions, while G is the planar graph itself, the whole thing as itself. For the next part, I will explain to you guys regarding Kuratowski theorem. This theorem was developed by Kazimierz Kuratowski, who is a Polish mathematician. This theorem was published in 1930, and this theorem provides graph quantization by identifying forbidden graph. This theory divides the planar and non-planar graph more clearly. This theorem states that a graph is non-planar if and only if it contains a subgraph homeomorphic to either K5 or K33. And you must be wondering what is homeomorphic. Homeomorphic is the possibility to change a graph by adding vertices along the edges. And any graph that have the homeomorphism or homeomorphic result of K5 or K33 is not counted as a planar graph. And in this segment, it is shown that K5 and K33 subgraph are the smallest graph structure that are out there. K5 is a complete graph with 5 vertices, and K33 are complete bipartite graph with 2 sets of 3 vertices that are adjacent to each other. The K5 cannot be a planar graph. This is because if K5 are drawn in a plane, it is impossible to draw it without any edge crossings. And this is the first violation of planarism of a graph. And the same of K33. There are no possible way to draw K33 without any edges crossings. And thus any graph with subdivision or subgraph of K33 and K5 are not a planar graph. And in this slide, I will explain to you guys regarding homeomorphism or homeomorphic example of a graph. As we can see here, by adding a vertices into the edges of a graph, we will change the number of edges and vertices. However, it is still a homeomorphic example because homeomorphism allow for various transformation, including adding and removing vertices or edges. As long as we do not create a new crossings or violate any planarity of a graph. The key is to maintain the topological value or relationship between the edges and the vertices. This also applies to the regions because no matter how many no matter if we change the number of regions, it will still become a homeomorphic graph if we do not create a new crossings or violate any planarism of a graph. In summary, you can change the number of regions, vertices, or edges as long as we do not create a crossings or violate others' planarism of the graph, and we keep the topological value. Thus, if any homomorphic of K5 and K23 are a subdivision of a graph, it cannot be counted as a planar graph because it contains a graph that have crossings no matter how many way you change it.
As for the application of planar graph have a lot of usage in solving problems and understanding it, where it consists in optimizing certain solutions to make it more efficient. Here presented some real-world examples, urban planning and molecular chemistry. For urban planning, planar graph offer a various tool for modeling and analyzing various aspects of urban planning, such as transportation network, thus allowing planners to analyze layouts, minimize congestions, and enhance the network system for the urban planning, making it more efficient in planning more map circuits and networks. For the molecular chemistry, planar graph can be used to visualize reaction paths and understand the changes in connection throughout the chemical process, where it can also assist in predicting the products and the intermediates. Continuing on the applications of planar graph, here we are presenting another two real-world examples of planar graph applications. There is geometry and topology, and the other one is computer graphic. In terms of geometry, planar graphs can be used to represent a set of points in the plane of von Neumann diagram, where the vertices and the edges represent the von Neumann areas and bounds. It also been used for map representation in this context. Vertices represent the regions or territories, and where the edges represent the boundaries of the territories. This application also related to the four-color theorem, where each regions are being colored with at most four different colors, in such way that no two adjacent regions have the same color. Okay, so as in for topology, planar graphs are being used in topological analysis, where planar graphs are valuable for topological analysis of meshes. It is to understand the connectivity structure that can aid in tasks like identifying boundaries, detecting holes, or analyzing the overall shape of a 3D object. The next one is computer graphic, where planar graphs are being used to represent the meshes in computer graphics. Triangulating the planar graph involves decomposing of 2D or two-dimensional space into triangles. As you can see in the slide, there's a picture of a dolphin that consists of the collection of the vertices, edges, and the faces that define the shape of a 3D object. These applications are particularly useful in 3D modeling and computer-aided design, or CAD applications. From the study of planar, we learned that it can be utilized practically and theoretically, where it assists in designing and structuring from the practical view, and also becomes a fundamental in graph theory from the theoretical view. In conclusion, analyzing specific planar graphs involves considering Euler's formula, Kuratowski's theorem, phases and regions, the four-color theorems, and also the graph connectivity. This analysis provides important information and valuable insights to determine the characteristics and the structure of the planar graphs. This proves that The study of planar graphs can also be implemented in practical implications across computer science, other related fields, and disciplines.